y hat gives us the orthogonal projection of y onto u, right? And yeah. So I actually did it with that on the board. So the orthogonal basis for W so basically, instead of just having one right here, we're going to have more vectors. Suppose that, but we're starting off with an orthogonal basis. So that whole thing, we're not just having one, we have multiple, right? So we're rewriting Y is an orthogonal basis for all of that stuff. So we don't need to find another, well, we kind of do need to find what Z is. So we're still going to be using that Y equals Y hat plus Z, where Y is in the span of whatever we want to find it in the span of, and Z is that orthogonal projection. So this, and what we're going to see like in the notes is we're going to basically find this U1, and all this other stuff is going to be Z. Okay? That's basically where we're going with that. Okay? Or we can use the first two, we can use the first three, right? It doesn't really matter which ones you use, you just kind of read what they give you. Okay? So that's what we're going to do for each Y and W. And then what we have, if that is an orthogonal basis, remember that all these are just scalars. That first part, that's just a scalar. And so we're going to take that scalar and change the magnitude of each of those vectors when we have an orthogonal basis. So if U1, U2 is already the orthogonal basis, let W be in the span of U1 and U2, U1 and U2 only. Write Y write Y in R3 as the sum of the vector Y hat in W and a vector Z in W. So how would we do that? So just like we did before in 6.2, how do we find the Y hat if Y hat is in U1 and U2? What are we going to do with that? Exactly. No. It's in the span of U1 and U2. So Y would equal. So I'll actually use this. How do we find Y hat? Right, but how do we find that alpha? So you're correct, but how do we find alpha? Y dotted with, yeah, U1 over U1, 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 right? And then plus, not minus that. So we still need to, so Y hat has two vectors in it. Yeah, Y times U2, dotted with U2, U2, and then U2. So there it is, right? So again, these are just scalars of the sum of vector in Y hat and a vector Z that's perpendicular to it. But if I just multiply by a scalar, do I need to do anything to find Z? It's a leading question. Do I do anything to find Z? No. Because that new one is going to then still be perpendicular to it. Because remember, that's just a scalar. And so I could use those. So if I change the magnitude of one of them, it really doesn't matter. So I'll actually write that up on the board using the example that we had before. So Y dot U3 over U3, U3, 3. So remember, these are just the scalars. And you called it alpha 1. So in the notes, we're just calling that our first constant, and we're going to call that our second constant, and this is going to be our third constant. Okay? So what I'm saying is that what you said was right. All we're doing is changing the magnitude. So before I start recording, for those of you listening, so we have this vector 6, 2, and we have the orthogonal basis of 2, negative 6. That's orthogonal to it, right? Those two vectors are orthogonal. And even if I change the magnitude of one of them, they're still going to be orthogonal. And you can kind of see that 6 and negative 6 is still 0, right? So we don't have to do anything special to find the z in this case, if we're starting with an orthogonal basis, right? So show that z is orthogonal to every vector in W. To show that, we need to show that z is orthogonal to the vectors in U1 and U2. So we are calling, so actually we need to go back. I just want to just clean that up just a little bit. So this, I'll use my green thing right here. This is the z, right? So that's the z vector right there. So y, and that's the vector z. So we found y hat, we found z.
Wait, but in the last thing, wasn't z just y minus?
Yes, it was, because those two vectors that we were dealing with were not perpendicular. We only were dealing with one vector. We were just dealing with like 3, 1. Okay? So when we already have orthogonal vectors, we don't need to do anything that's special in that case, right? So those two vectors, 3, 1, and 8, negative 4, they are not perpendicular. Okay? So we do need to do something special to find z. In this case, we don't. Just got to be clear with what we have. So how do we find that z? So in that case, what is z? And in the other case, we will have to do something a little bit. We could do the same thing, and we could do it a little bit differently, honestly. So what is z dotted with U1? Well, what is z, though? What was z in that case? So in that other example, what was... Yeah, it was alpha 3. So z, from that, I guess technically was green, right? So what was the vector that we used for z? No, for this example with all of these right here. So I'm saying that z is this thing right here, right? So so we want to find, so if they are orthogonal, then what is the dot product going to be? 0. Right? But now we have to define what z is from that last example. How do we find z? What was that defined as? Y dotted with U3 over U3, U3. Right? That is what z was. Right, from that last slide, dotted with U1. So again, we're starting with an orthogonal set. So therefore, this is just going to be some scalar. Okay, all we did is change its magnitude. And when we do that, it's still going to give us 0. Oh yes, I did leave off that U3. Thank you. So that is what z is. Yeah. So it's that. So it's a constant times a vector, and so that does give us a new vector. Sorry. I was like, yeah, I knew there was something missing. Thank you for catching that. So it's going to be the same thing right here. So y U3, U3, U3 times U3, not dotted with U3. Okay. So that is just a vector. All it is changes magnitude, right? And then I'm going to multiply that. I'm going to dot that with U2. So the key here is that in the background, and it's not easy to see with just variables, U2 and U3. So this was already, the dot product was already 0, honestly, right? It doesn't matter which one you do, and that's just the scalar, right? So this is the scalar right here. So this was already 0. So any number times 0 is still going to be 0. Okay? So let's look at an example right here. So this, the numbers are 4, 5, -3, and +3 for V. Okay? Write V as the sum of the vectors, the sum of two vectors. One that's in the span of U1, and the other that's in the span of the other three vectors. So there are two ways that we can do that. So we can go back to the old way, or we can do kind of the new way. Right? It really doesn't matter. All right, so how do we find one vector that's in the span of U1, but I want to use V? Okay, you're 100% correct, but let's go ahead and check. What is the title of this unit? Still orthogonal sets, right? One of the first things that we are going to do is we're going to give you multiple vectors, multiple data sets, and we can still check that U1 dotted with U2. What is that? Just by inspection, what is that? 0, right? That dot product is 0. And we can check that U3 and U4 is going to give you -1, +1. That's 0. Then we have -2, +2. That's going to give you 0. And you can check the other however many combinations that we have, right? But they're all going to give you a dot product of 0. We're starting off with an orthogonal set. Okay? So we have something that is in R4 that we cannot graph. We can graph R3 because that's just plain, right? But all these vectors are orthogonal, and they actually have a basis in all that jazz. Okay? So one's in the span of U1. So how do we find that vector that's in the span of U1? What are we going to do? U1 to V, right? So it's going to be V dotted with U1, 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 U1. And so that is going to give us what? What's V dotted with U1? Yes, I hadn't done that. So, what? 14. Okay. So, 14 over, what's U1 dotted with U1? U1 dotted with U1. That's okay. 4, 5, 6, 7. So it's going to be 2 times U1. All right, and now, so since it's going to be 2 times U1, that is just going to be 2, 4, 2, and 2. So we have a vector that's in the span of U1. How do we find that vector that's going to be in the span of U2, U3, and U4?
We just have those three vectors and write the equations as y or z equals the first vector plus that.
Yes, that's it, right? So the other one that's in the span, we're really finding what z is, right? So this is the y hat part plus this other vector that we want equals v. And v is 4, 5, -3, +3. So now we can very easily find out what z is. The other's in the span of that one, right? And it didn't matter which one we did. So on that other one, we were dealing with 3 vectors, and we had one that's in the span of 2 of them. So you could do that U1, U2, U3, right, and look at all those vectors and then add those up, or it's the same thing that we did before. Y is equal to y hat plus z. But we don't need to find any, this z is already orthogonal. So we don't have to do any of that crazy, we don't have to do any fancy math on that. Okay? So Z would obviously now be, what is the top number that we need to find? What would that be? 2. The next one is 10, -5, and okay. So that's it. So that times that. Okay. What happened? But we found out the number that's in the span of that. We found that out. So what we did before, yes, you can double check it by doing what? Yeah. But yes, you can double check it by doing Jesus and finding out what those things are.
Okay. We just did it by inspection.
Yes, we did it by inspection. Okay? So what we're saying is that
We're just going to assume that vectors in the span of the other two.
right, yeah, but we could still do that, right? We could also do that C. What is the other way we could have done that? What would Z have been? Had we done it the other way? What's the other way if it wanted to be in the span of U2, U3, and U4? Add what? What are we going to add? Right, and so that is going to be, so what would that be? And we can just, oh, no, we can't do it. B dotted with U2, 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 plus B, U3, 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 3, plus B dotted with U4, 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 right? So we could do that if we really wanted to, okay? So this is going to be a lot of arithmetic, honestly, with all this stuff, and a lot of fractions to be comfortable with. Some of them, a lot of times, they're not going to give you a fraction of 14 over 7. Okay? So we just have to be just careful with our arithmetic and double check our work. Okay? So now we have this orthogonal, and so that is the same thing that we just did, basically. We found y hat, we find the orthogonal projection. The orthogonal decomposition. So y is still, it's really the same thing. Y hat plus z, where y hat is in W and z is perpendicular to it. Perpendicular to it. Okay? So if we have an orthogonal basis of W, which we're starting off with in this case, and then we'll make it harder in the next section. So y hat is just going to be the sum of all those scalars dealing with y. We find the scalar and then multiply by its corresponding vector. Okay? So that's how we find y hat. Okay? We need to find this one. And what we're going to multiply that one by, this one will be basically given to us, and then we can figure out what z is. And that's really what we just did in that other example. Okay? So y hat is, again, the orthogonal projection of y onto w. But in this case, we have two vectors, right? The other one, in the last section, we just had one vector for that orthogonal projection. So we have W that's made up. W is made up of these vectors, right? Whatever those vectors are. Okay? And we're finding that orthogonal projection, which is going to be the least squares. We're going to use that later for the least squares solution, like the closest point. So we have a vector y that is not in W. So what would be, how can we make this closest vector that's going to project down onto that plane? Okay? So, verify that U1 and U2 is an orthogonal set. Okay? So is that cross product, is that dot product 0? And yes, it is. It's because we have 0 minus 1 plus 1. That's the dot product of U1 and U2. Okay? Find the orthogonal projection of y onto the span of both of them. So how would you find that orthogonal projection? What are we looking for? Exactly. We want to find out what y hat is. Okay? So y hat is going to be y dotted with what? U1. And then we're just going to write U1 a bunch of 3 more times. And we're going to add that to the U2 stuff. Okay? And that is that, basically. So take a couple seconds and figure out what that is. Or what was y hat give you. So you will have some fractions on this one. In the individual ones. U1 is going to be 18. And U2. Oops. It's going to be U2. Right? So those are kind of the numbers that we're going to use for that. So, what is y1 dotted with u1 over u1? What does that give you? So we got negative 27 over 18 u1, and that obviously reduces to negative 3 halves. And this is going to give you 5 over 2. I already gave you the U2. And so that gives you, so there are going to be some fractions in there, but when you add them together, you don't get fractions. And so y hat is going to be, what? What do you get on that one? Huh? No, because that's a 3 halves, not a 5 halves. I don't know what you were. Yeah. Oh, yes, so y hat is going to be what, actually? Yeah, it's just still going to be that same thing. It's going to be 641. Okay? Are we good? Then when you do that, that's what you get. Okay? Right, y is the sum of a vector in W and a vector orthogonal to W. So we're starting off again with an orthogonal basis because the dot product is 0. Okay, so it's going to be the same thing. So in that other one, we didn't find the orthogonal. So what do we write y as a vector in W? What are we finding when we're finding a vector that's still in W? What is that? What is our name that we use for that? Y hat. Okay. So, and actually going back to the other one. And a vector orthogonal to W. So we got to find out y hat. So what is y dotted with u1? What is y dotted with u1? 10. And then u1 is also 10. So we're going to start off with u1. We don't have to do anything special to that. And y dotted with u2 is 3. And u2 is going to be 1. So really all we have to do is add u1 is going to stay, and this is just going to be a 3 right there. So y hat is going to be 3, 3, 1. Okay? So that's what y hat is. Now we got to find the vector that's orthogonal to w. We want to write y as the sum of that. So now it's pretty easy. Yes? So we know that y is 0, 3, 10. So 0, 3, 10 equals what we had before, 3, 3, 1 plus -3, 0, and 9. And again, now those two vectors are orthogonal. They're orthogonal to W. Okay? So it is going to be -3, 0, and 9. So we're going back up here, just double checking that we did it correctly. -3, 0, and 9. This vector is orthogonal or perpendicular to W. Right? And W, all we did is just basically put scalars on those. Right? And we can double check we did that correctly because z dotted with u1 is, what's z dotted with u1? 0. And z dotted with u2 is also 0. Right? Because it's 0, 0, and 0. And z dotted with u1, yep, also equals 0. Right? Dot product is 0. Good? Alright, so just like the last one, then we'll be about done. Those orthogonal projections, that's what we're doing. We're finding those as they're going down to each one of those vectors. Okay? So that's what we're doing. We're finding that least squares solution. We're finding the best approximation for that. W be a subspace in Rn. Y is any vector in Rn. And y hat is the orthogonal projection of y onto W. Then y hat is that closest point to y. And y hat is staying in W. So y hat is in W. So this is that vector-ish, or actually not that vector, excuse me, we're going to go from 0 to y. It's where we find that point that's in y. And that's the closest point to y. So that y hat is in W. Okay? We have two vectors that make up that. Okay? We want to put it right underneath it, basically. Okay? So that it's closest to all those things in W. So, and it's the same thing that we did before, where we had the square root of 40 in that case. We found that closest point. We found the magnitude of that. We did y minus y hat up here.
What is V?
V is
So for all of the
V in W, right? All those vectors that are in W. So that plane is made up of a million vectors, maybe more than a million, maybe 3 million using random numbers. Yeah. So we're not going to do that proof. Just going to skip that one.
Are we in matrix this year?
No. find the closest point to y. So we have this y that's just this vector. We really can't graph that. Well, we can't graph that vector. Okay. Find the closest point to y that's still in the span of u1 and u2. Okay. We're good. So, what are we going to find? What's the first thing we got to find? Like for the 12th time in a row.
Y hat.
Exactly. Right. So we got to find out what y hat is.
If it didn't have span U1 and 2, would it then be just Z component?
Mm-hmm. Yeah, but yeah. And those, and what's so special? What is special about U1 and U2?
XY plane?
No. What's so special about those two vectors? Exactly. Right. We're in that section. It's called orthogonal sets. So that dot product is 0. All right. So that's just using terrible notation, right, inside of that. So that dot product is 0. So we already have an orthogonal set. So we need to find out what y hat is. So y hat would obviously be what? Now we have two vectors, right? We have to take consideration both of them. It's going to be y dotted with u1 over the same freaking thing again. And we're going to add that to y dotted with u2 over u2, u2, u2. So, yeah, so that u1 dotted with u1 is going to be, both of them are going to be 2, kind of obviously, right? So that's going to be 2 right here and 2 right here. And y dotted with u1 is going to be 6. And y dotted with u2 is going to be -2, right? So y hat is just going to be, so these top numbers are 0 for u2. So really the only thing that matters is this 3. So 3 and 3, right? Double checking my math on that. And now we have, hold on, 0 and -2. And -2. Okay? Oh, -1. So it's -2 over +2. So thank you for that. -1, -1. Okay? That's what y hat is. So that's the closest point. Right? Still in y. It's still in the span of that. We're good? So z is the projection, so therefore it's not going to be in u1 and u2 anymore. It still has to be in the span of that. So we're not finding z in that case. We're finding that point that's kind of right underneath y. And that's it. Really. That's the most important stuff for 10.3. I think that's all I really wanted to cover today.
Like comments.